Hey guys, welcome to Tom's SAT. Today we are learning quadratic equations, and if you guys have gone through Algebra 1 and Algebra 2, you know that there's a lot of things to find out about quadratic equations. But so for today, we're only going to focus on the three different forms of what quadratic equations look like and how they relate to the graphs of quadratic equations. So first, we're going to go through the basics of quadratics, learn some terminology, and then we're going to understand the relationships of standard form, vertex form, and intercept forms, and how they all relate to graphing a quadratic. And then we're going to talk about how these three forms relate to each other, and then how to use a calculator to do some basic stuff for quadratics, and then we'll try two tough problems today. So first things first, let's learn the basics of a quadratic equation. So the basics of a quadratic equation, we're going to experiment with y equals x squared here. And I have a table of x and y values that we're about to find. So first, let's plug in 0. If I want to plug in an x value, it's this, right? Remember to put it in parentheses, and then we square. So y is equal to 0. If I stick 1 in there, I'll get a 1. If I stick 2 in there, I'll get a 4. If I stick a 3 in there, I'll get a 9. And with that, we now have 4 points. And now we're going to try to find the 3 points to the left of these 4 points over here. And we're going to stick a -1 in there. And if I stick -1, remember that the -1 is in parentheses before we square it. So if you take a -1 squared, you'll get a +1. So keep in mind that anytime you square a negative value, it's always going to come out as the positive version of the number. So then we have our 3 points to the left. And now that I have these points graphed, you can draw a rough curve through all these points to kind of give us a rough gist of what the parabola looks like. So then what you'll notice is that we make like this U-shaped curve, and this U-shaped curve here is called the parabola. And anytime you graph a quadratic, you're going to see a parabola pop out of it. And you should be noticing two things that are happening with this parabola here. One, it is a left-right symmetrical, as in you can see there's a line occurring down the middle here. And the left side of this line is a mirror image of the right side of this line. And parabolas are always symmetrical that way. Also, individual terms are being squared. And that's how you know that whatever value that pops out of x squared is always going to end up being the positive version of that number. And you can recognize that you're dealing with a quadratic through two things. One, the equation or the function you can recognize as a quadratic because the x has an exponent of 2. And when you're looking at a graph, you recognize it's a quadratic by noticing the shape of the curve, as in it's like a U-shaped curve, also known as if it has the shape of a parabola. And that is the general behavior of quadratics right now. And now let's learn a couple key terms before we move on. So this right here is a quadratic equation, and we're going to figure out how to name some of the points right here. This point where it intersects with the where the function intersects with the y-axis, this is called the y-intercept, and it produces the point where when the x value is 0, the y value is your y-intercept. And this point on the very bottom here that you'll notice is the point that the line of symmetry goes through, so that the left side and the right side matches each other. This point is called the vertex. And what it produces is the point with a minimum or maximum y value of the parabola. you'll notice, and when we say min and max, we mean the min and max of the y value. So you'll notice that in this case, in this parabola that's going upwards, the vertex is going to be your minimum point. Whereas if I had a downward facing parabola, the vertex would be the maximum. And last thing I want you guys to take notice right now are these 2 points where the function is intersecting with the x-axis. And this is one of the most important concepts with quadratics because you're asked about it a lot, and it has 3 separate names that all mean the exact same thing. Now, looking at the graph, you recognize it as x-intercepts because it's where it intersects with the x-axis, but also it carries the nicknames of zeros because these are the x values where when you plug it into the equation, the y value becomes 0. So these are also called zeros, or in terms of quadratics, they're also called solutions. Because if you just plug in the x value and then 0 into the equation based on these points, then you'll know that then you'll have a solution for the quadratic equation. And in different quadratic questions, they'll ask for they'll use different words to ask for the same thing, and you have to remember that all 3 of these terms are exactly the same thing. So the methodology you use to get to these 3 seemingly different answers is the exact same method. As long as you know how to get to one, you know how to get to the other 2. So for the purpose of simplicity for this lesson, I am going to be describing all my x-intercepts as zeros. And that's basically the same thing as me saying x-intercepts or solutions. I just like zeros because it rolls off the tongue and it's easy to describe. And these are a couple basic terms. Now, as you probably guessed, most quadratics don't just look like the first one I showed you in the example. The parabolas of quadratics, they shift, they get steeper, they get wider, they face up, they face down, they shift left, right, up, and down. And this is the lesson where we learn how to describe all those changes compared to the basic y equals x squared parabola. And with that, let's go into our first form of quadratic equations, which is the standard form. The formula for standard form is y is equal to ax squared plus bx plus c. Now, you already know that the x and y are the input and output for an equation like this. So then the values that determine how the graph shifts are a, b, and c. And using those 3 values, we can figure out quite a few things about the graph if we just have them memorized. So first things first, we can figure out whether the parabola is going up or down based on whether we have a positive value for a or a negative value for a. Positive means it goes up, negative means it goes down. Another thing we figure out is the steepness of the graph. You can think of it as the growth rate of the graph based on the a value. The further away a is from 0, the steeper the graph is going to be. The closer a gets to 0, the wider the graph is going to get. So to show you like a quick example, if this is your standard parabola where a is equal to 1, an a value of 10 is going to give us a much steeper looking parabola, and an a value of, let's say, 0.2 is going to give us a much wider parabola. And that's what I mean by growth rate. And now we're going to talk about a couple other things we figure out with a standard form. Another thing that's really, really easy to get from standard form, and I say easy because it's literally visible to us right now, is a y-intercept. And the y-intercept is when you plug in, is when the x value is 0, what the y value is going to be. In standard form, you'll notice that if you plug 0 in for x, this part zeroes out, this part zeroes out, so then y just ends up equaling c. Which is why when I'm dealing with a y-intercept, I know the x value is going to be 0 and y value is 100% already going to be c. And the last thing that we figure out from standard form uses a bit of a formula, but it's absolutely doable as long as you remember the rule and the formula for it. So for a vertex, we need an x value and a y value. The x value is always given by the formula of negative b over 2a. As in whatever the b value is, take the negative version of it divided by 2 times a. And that's going to give you the x value of the vertex. And you should know now that anytime you have an equation and you know the x value, you just plug it into the equation to get the y value. But and in this case, it is no exception. If we plug negative b over 2a into the equation, the y value that's supposed to be there for x will just pop out automatically, and that's going to give us the y value of the vertex. Now, I know I'm writing it as f of negative b over 2a. It's not technically correct because this is function notation and we're dealing with an equation here, but this is just me trying to show you that whatever value you get over here, you just plug it into the equation to get this value. And standard form shows us these three things really, really quickly, and using this can help us graph most equations relatively easily. So let's try an example right now, and we're going to get something like 2x squared plus 8x plus 9, and we're going to work on graphing this, even though it looks like a mess to graph. So first things first, I already know that this thing is going to be facing upwards because the a value is positive. I know that my y-intercept is going to be 0, 9, but first, and you should always do this when you're dealing with quadratics, you should write out what a, b, and c are. A is equal to 2, b is equal to 8, and c is equal to 9. And I know that the y-intercept is going to be 0, 9 because it's supposed to be 0, c. And now I got my first point. And my vertex, I can find the x value. By doing negative b over 2a. So then in this case, I'm going to get negative 8 over 2 times 2, which is negative 8 over 4, also known as negative 2. And now to find the y value, I just got to stick the negative 2 into the equation. And that's going to give us a positive 1. And now with that, I know that my vertex is going to be negative 2, 1. And this might not feel like a lot right now, but I actually have the ability to draw a fairly accurate looking equation right here, right now, simply because I know that the vertex here is this point, and it's going to be an upward facing curve because a value is positive. So I know I'm going to go from the vertex to the other coordinate I know, just like that. And if you're not sure how to graph the left side, remember that these equations are left-right symmetric, and the line of symmetry goes through the vertex, so that I know that another point that's to the left of the vertex is going to be this green point right here, where the y value is the same and the x value is equidistant from the vertex, 2 units away. And with that, I have a really, really easy way of finishing the rest of this graph. Ignore how bad that curve looks, but that's how we do that. And notice that in this particular situation, in this equation, I don't actually have x-intercepts, and that is entirely possible. If your quadratic does not intersect with the x-axis, that means you don't have x-intercepts, and that is a viable option for quadratics. And with this knowledge in mind, with this set of rules in mind, we are going to try our first example. So I have if f of x equals x squared and g of x is equal to x squared minus 6x plus 14, which of the following best describes the graph of g of x relative to f of x. So when they say describe the graph of g of x relative to f of x, they're asking, how did I get from f of x to g of x? And you can tell with A, B, C, D here, they're just talking about how the graph shifts. And one thing you guys should know right now is that graph shifting is, if you know that the behavior of the graph is the same, then it's the same thing as just shifting the vertex. So to show you an example, if I have to take this quadratic right here and I want to shift it over 2 units and then down by 3 units, the way most people think of how to do that is they think of taking each one of these points, and there's like an infinite number of them, right? And we shift them all over 2 down 3. So that this is a new point, 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 this is a new point. And after shifting over all those points, we have our new parabola. But that is actually a really, really troublesome and not useful way to think about how to shift graphs. When you're shifting graphs, you should be thinking of shifting it based on the vertex. So a different and better way of thinking of how to shift an equation, supposing that I want to move it 2 units to the right and then down by 3 units, is I want to figure out where the vertex is. And I'm going to move that vertex 2 units to the right, down by 3 units. And now all the behavior of the rest of the points simply follow where the vertex is going. And with that in mind, instead of trying to figure out how that graph shifts from x squared to x squared minus 6x plus 14, I really just need to figure out how I shift the original vertex of 0, 0 to the new vertex of whatever g of x has. And knowing that we're only looking for the vertex of g of x means that we can employ our basic formulas for finding x and y values in order to do this problem. So I'm going to write A. So first, you should always list what A, B, and C are. A is 1, B is -6, C is 14. And I know the way I get my x value is negative b over 2a. And then that's going to give us -6 over 2 times 1, which is equal to -3. And now we go in and plug that -3 into the equation. And we're going to get something like 9 plus 18 plus 14, which is like 56 or something. And now you're looking at these answer choices and you're like, well, none of these seem to have a vertical shift of 56. So what seems to be the issue here? And the issue is that I didn't match the formula up correctly. Some of you may have noticed this already as I was going through the problem. But if b is already -6, that means that I'm actually taking a +6 and dividing by 2, which means that this result should be a +3. And I have no doubt in my mind that some of you missed this step because you're just sticking 6 into the formula. The reason why I say it's so important to write out what A, B, and C are, even though you're looking at the numbers right here, is that you have to take an extra step to think of how this equation translates into what these variables are, as opposed to just writing it out in the first place so that when you go put it through a formula, you're really just copying your work. You're copying numbers down instead of taking an extra step in your head. And that doesn't feel like a big deal, but it absolutely is. And with that, we know that the x value we want is actually supposed to be a positive 3. Put it through the equation, and I'll get my y. Which is going to give us 5. That's how I know that my vertex is going to be the point of 3, 5. And now, trying to go from 0, 0 to 3, 5, I can really easily picture that I need to move over right by 3 and then up by 5, which matches my answer choice of B right over here. So finding the new vertex and then describing that horizontal and vertical shift is how you figure out how one function shifts into another function. And now we move on to the next form, which is going to be the vertex form. So the vertex form of quadratics is y equals a times x minus h in parentheses squared plus k. So this one looks very different from a standard form, and there are some similarities that the formulas give us, and there's some differences in what the formula gives us. So in terms of similarities, it still tells us whether it's going up or down based on the sign of A, and we can still figure out the growth rate, as in how steep or wide it is, based on the value of A. And that's about where the similarities stop. Even though this is not as easy to reach as with standard form, the y-intercept is also relatively easy to find because the x value is just going to be 0. And if the x value is 0, you can always find the y value by simply plugging in x as 0 into the equation, and then whatever value pops out is your y value. So y-intercept is never really that hard to find. And that's even if you're dealing with vertex form or the other form I'm going to show you later on. And the last thing is probably the most important thing. Guess what the vertex form tells you? If you guess vertex, ding ding. Okay. What the vertex form gives us is the vertex, where the x value of the vertex is going to be h, and the k value of the vertex, the y value of the vertex is going to be k, based on this equation. Remember that the letters can change, but it's really more about the positions of where all the numbers are that tells us whether we're dealing with vertex form or standard form or factored form. And with every vertex form we see, we get all this information right over here. So with that in mind, let's try an example really quick. Let's try to graph an example really quick, and then we'll discuss. So if I have something like y equals 2 times x minus 3 squared plus 5, we know that the curve is going to be going up, and it's going to be steeper than usual. The vertex, I know that the x value is supposed to be h, so this is supposed to be x minus h, so then the x value is simply the 3. So x is 3, and the plus 5 here matches with the formula where it says plus k, so then the 5 must be the k, which means the y value of the vertex is 5. And so with that, I already know that the vertex of the equation is right over here. And if I want to find the y-intercept, I just need to plug 0 into the situation. And That's going to give me negative 3 squared, which is 9, times 2 is 18, plus 5 is 23. So then the y-intercept would be somewhere up here. And if you want to draw this curve, you know that the other point is going to be equidistant to the vertex as the first point that I just found. So if 0, 23 is 3 units away horizontally from the vertex, that means it's the same horizontal distance from the vertex to the other point. So this right here would be 6, 23. And then we can graph this pretty little quadratic. And now we have a graph. And before we move on to a problem, I want to show you another example that's really important to be aware of. So now let's deal with y is equal to negative 2 times x plus 1 squared minus 3. So for this equation, it's really easy to figure out that it's going down. Finding the y-intercept is not going to be that hard because we just shove 0 in there. So 0 plus 1 is 1, squared is 1, times negative 2 is negative 2, minus 3 is negative 5. So 0, negative 5 is my y-intercept. Now, if you want to get the the vertex, it gets to be a little bit different than usual. So let's just talk about finding k first. You'll notice that in this equation right over here, even though it looks like the vertex form, it doesn't quite exactly match up to y equals a times x minus h squared plus k. I know instinctively that you want to say the 3 is the k value because that's the number at the end. But if you notice that it doesn't match this formula, then you can't say this is automatically going to be k. What you have to do is rewrite the equation so that it matches the formula of plus k. So instead of writing it as minus 3, I would have to write it as plus negative 3 so that the y value is going to be negative 3. And same thing with x plus 1 here. I know the instinct is to say, oh, the x value has to be 1. But it has to match the x minus h squared formula in order for us to use it. And for us to match it with the x minus h formula, I would have to write x plus 1 as x minus negative 1 squared. And now that it matches the vertex form, we can actually tell that the h value in this case is supposed to be a negative 1. And with that in mind for our vertex, we can graph this. Graph our y-intercept. Know that the same y value is going to pop up on the other side of the vertex, and then we can graph this little graph, and it's nice and easy. So I wanted to show you this example just to show you how important it is to be able to match your situation to your formula, and get you to get comfortable with the understanding of horizontal and vertical shift. The vertex form doesn't tell us a lot in terms of, it doesn't tell us a lot more than the standard form because the vertex we can find really, really easily. But what it does tell us is the vertical and horizontal shift from a basic equation like y equals ax squared, because it's moving the vertex left and right, up and down. Now the k value here, if it's adding, then that means it's going up. If the k value is negative, that means it's going down. And the h is in charge of a horizontal shift, where when the h value is positive, instead of moving to the right, it is actually moving the entire equation to the left. And when h is negative, it actually moves the equation to the right. And you'll notice that with both examples we tried, when I did x minus 3, whereas it normally would have started right here, the equation moved right 3 and then up 5. And then for negative x plus 1 squared minus 3, whereas the normal equation would be here, we moved it 1 to the left when it said plus 1, and then down 3 when it said minus 3. And that's what vertex form does for us. And with that knowledge, let's try an example. Okay, so question B here tells us that the vertex of the parabola in the xy plane above is 0, c. So this point right here is the 0, c. And they're asking us which of the following is true about the parabola with the equation y equals negative a times x minus b squared plus c. So these are our 4 options. It's telling us where the vertex is and telling us whether it moves up or down. Now, if you notice that y equals ax squared plus c is upward facing parabola, so then that tells us that the a here must be positive. So if I decide to turn it negative now, that means for sure I have a downward facing parabola, which means option A is gone and option C is gone. And now I'm just left to choose between B and D. And guys, this is one of those moments where you can either do this the long way, which is annoying and difficult, or the easy way if you have the formula memorized. If you don't have the formula memorized, you might be inclined to write this whole thing out or plug in numbers in for B and C so that you can analyze what is supposed to happen with the equation and use that to find your vertex. But if you simply match it to the formula of y equals a times x minus h squared plus k, and you know that the h and k don't really have to be h and k, they can be any other letters and mean the same exact thing. If you just match them based on form, you know that the vertex is supposed to be h, k, so then in this case, the vertex is supposed to be b, c. And this is one of those situations where it's not so much the skill, but if you just have the formula memorized and know what everything is supposed to mean, you can get to that answer within 10 seconds. And that's a good way for you to use vertex form. And now we move on to intercept form. It's just like vertex form, it gives you what the title says it does, but it doesn't give you the y-intercept directly, it gives you the x-intercept directly. And first, let's talk about some similarities it has with the other two. You'll notice that besides x and y, the letters I have this time are A, P, and Q. So the A here does the same thing as the other two forms, whereas it tells you whether it goes up or down. And it tells you the growth rate of the parabola. And the other thing that you automatically already know is that, not automatically already know, but another thing that you can find is the y-intercept, where you literally just stick 0 in for x, and then whatever, and then once you do the calculations, whatever value you get out of plugging 0 into the function is going to be your y value for the y-intercept. And it tells you one more thing that's extremely important, and which is it tells you where your zeros are going to be. And this is the first and last time I'm going to remind you that zeros and x-intercept and solutions are literally the same thing. And and the x-intercepts or the zeros or the solutions that you find is based on P and Q, as in x is equal to P and x is equal to Q. If you decide to write it like this, it's also viable. So a rough drawing of a intercept form is maybe a situation where you have this, where these 2 points would be x equals p and x equals q. And this form gives you the zeros, which is going to be a lot of what quadratics is all about when you're dealing with the SATs. Okay, so I drew this really rough graph, this really rough quadratic that goes through our 2 zeros here. But you may notice that this is still a parabola where the vertex is roughly over here. And what you should remember about a vertex is that it's literally the center of the graph, meaning that the left side and the right side are symmetric with it. And with this, you'll notice that the vertex is the point that's right in between, right in the middle of Q and P. So this point is the vertex of the x value, and you should remember from the other forms that anytime you know the x value, the y value is right around the corner. So not only does intercept form give us all this stuff, we are able to find the vertex by knowing that the x value is always going to equal the midpoint of our 2 zeros. So the way to get the midpoint of those 2 values is to take p and q, add them together, and then divide it by 2. And that's how we get the midpoint. And if I want to find the y value of the vertex, as usual, we're just going to be plugging whatever p plus q divided by 2 is into the equation, and that will give us the number we need to get the y value of the vertex. And with that knowledge in mind, let's try a couple examples. So the example I'm trying to graph here is y equals -2 times x plus 2 times x minus 4. So first, I know that this has to be a downward facing parabola with a growth rate of 2. And now I want to find my first 2 coordinates with my 2 zeros based on x plus 2 and x minus 4. If I try to match this to the form of x minus p and x minus q, it is fairly easy to see that the 4 is one of my 2 values. So then 4 is the q in this case, which means x is equal to 4. Now with this one right here, x plus 2, you'll notice that this doesn't match the formula, so you have to write it to match the formula. Rewrite it to match the formula. So then this would be x minus -2, in which case x should be -2. Now that is one way to think about it that absolutely works, but the way I like to think about zeros is a little bit different, but I think a little bit easier to think about. What I like to do when I try to find zeros is remember that I am trying to create, if I'm trying to find zeros, I'm trying to find x values that's going to make the equation equal 0, which means if I make x plus 2 equals 0 here, the whole thing's going to 0 out. So what I like to do is think of what value do I plug in for x that's going to 0 out this factor of the quadratic here. And in this case, it's a lot, when you think about it that way, it's a lot easier to see x equals -2 is going to give me a 0 here, and x equals 4 is going to give me a 0 here. And with those 2 points, I can graph my 2 zeros here and here. And now I have 2 points figured out for this parabola. Now I'm going to want one more point, which is the vertex, in order to figure out how to really draw this curve. And the x value of the vertex, I know it's going to be a point that's right in the middle of these 2 points over here. And you can do this a couple different ways. You can do this through the formula by doing x equals -2 plus 4 over 2, which equals a +1. which is true. Or you can really just think about it as subdividing distance. This whole thing's supposed to be 6, so then I should be breaking, so the point in the middle should be 3 units away from each, which means that that coordinate should be, x coordinate should be 1. I prefer the graphical way to do it because that's one of those things where it's easier to see that way. But if you want to do it by formula, that works too. And now to find the y value, I really just need to plug 1 into the equation. So -2 times 1 plus 2 times 1 minus 3. This just simplifies into -2 times 3 times -2. Keep in mind the signs. That's going to give us a positive 12. And that up here is around where 112 would be. Label that as my vertex. And now we can draw this curve that describes everything we need to describe with it. And this is an example where they gave us the intercept form and we can graph them all, and we just graph it based on the x-intercepts. So there are going to be situations where when you graph out the equation, when you look at it, you think that it's possible to turn it into factored form in order to graph its intercepts. But if you understand what the graph looks like, your thought might change. For this example right here, I know that the curve is going upwards, and I know my vertex is at 3, 2. And if I have the point 3, 2, and I know that this curve is going to be going upwards, then what I notice is that it is never going to go down and therefore never going to hit the x-intercept. And if it is never going to hit the x-intercept, that means I don't have any zeros, which means there is no way for me to turn it into the factored form. And having an understanding that every quadratic you deal with ever is always going to have a vertex. It's always going to have a y-intercept is really, really important. But the x-intercept is something that shows up a lot, but not always. Therefore, the factored form of an equation does not always work. Because we know that the x-intercept doesn't necessarily always exist, that means the factored form of a quadratic does not always exist. And now that we have this understanding, let's try an example. So what is the vertex of y equals x minus 1 times x plus 3? If you're used to, if you don't know the rule about a vertex form of equations, you might be tempted to turn it into standard form and then turn it into, and then use the x equals negative b over 2a formula in order to get my y value. But if you remember that with vertex forms, they're automatically already giving you 2 coordinates, where you know that the 2 zeros for this situation are x equals 1 and negative 3. Then it should be really quick for you to recognize that then the vertex, which is the midpoint, which the x value is going to be the midpoint of these 2 points, the x value is going to be a negative 1 for my vertex. And now that we know negative 1 is the x value for the vertex, we simply need to plug it into the equation. And that's going to give us negative 2 times 2, which is going to give us negative 4. And really quickly, you know a is the answer, supposing that you remember that rule about the x-intercepts. Although for this particular example, I want to show you guys a slightly different way to do it. That's, I think, a little bit faster. Between these 4 coordinates, only one of them is correct for this equation. And you know, if I plug in 0, I'll get negative 1 times I'll get negative 1 times 3, which is going to be a negative 3. So D is a terrible answer. And now A, B, and C all have an x value of -1, so I just need to try plugging -1 into the situation, in which case I'll get -2 times 2, which gives me -4, and now I know A is a solution. Not all questions come this easy. I would say for the most part, you would do the vertex thing that I just showed you, but you got to recognize when they're giving you a freebie, and this is one of those situations. And now that we've learned all three forms of quadratics, let's talk about how they all relate to each other. These are the three different forms of standard, vertex, and factored forms. You'll notice that A is a similarity that all three formulas have. And then short of that, we have B, C, H and K, P and Q, which tells us entirely different things. So for all three formulas, we know that the A value tells us whether it's going to go up or down. And we also know that the A value is going to give us the growth rate towards how steep or wide it is based on how far A is away from 0. And that is where the similarities between the formulas stop. So for standard form, the most easy information to come by is the y-intercept because we're staring right at it. And the vertex is something you can remember based on the based on the formula of the standard form. And you can get your x value through -b/2a and then plug it into the equation to get what the y value of the vertex is supposed to be. For vertex form, the vertex is the easiest thing to come by because you just match it to the formula, and the x and y values are h and k, where h is the value being subtracted by x, and k is the value that is added outside of all this multiplying and squaring. And the y-intercept is the x value is obviously 0, and the y value is whatever you get by popping 0 into the equation. And for factored form, there's a couple things they tell us. The x's, the zeros, solutions, and x-intercepts, all same thing, remember, are easy to come by because they're just p and q. They're all the values that make one of your factors 0. The vertex is relatively easy to find because we just need to take the midpoint of p and q and then plug that into the function to get the y value of the vertex. And the y-intercept we can get easily by plugging 0 into x and then calculating to figure out whatever y is supposed to be. Now, in each one of these forms, there's stuff that is naked to you, as in you see it immediately, and then there's stuff that you have to do a little bit of work for. For standard form, the y-intercept is right in front of your eyes. For vertex form, the vertex is right in front of your eyes, and for factored form, the zeros are what's right in front of your eyes. And and then everything else are things that are relatively easy to get to, but you got to do a little bit of work for. And understanding what each one of these forms tells you about the function that you're dealing with is a big advantage whenever you're going through problems. And not only does it tell you what you do know, understanding this chart also tells you what you don't know, which is why you may need to shift. There are going to be times where you're dealing with this, where they're going to give you a standard form equation, and they're going to ask you for your zeros, and you're going to want to change the way your equation looks by turning it into the factored form. There are going to be times where you have factored form, and you want to see what it looks like in standard form. So then you want to rewrite this equation to match that form. And for that, I have a chart that shows you how to convert from one form to another. So we have the form standard form, vertex form, and factored form. For you to go from standard form to vertex form, you need to first find the x value for the vertex, which you know how to do, then find the y value for the vertex, and then you need to plug it into the vertex formula based on the way you memorize it. For you to get from standard to factored, you just need to factor the standard form that you already have until it looks like factored form. For vertex form, going to standard form, that's the easiest one. You just need to simplify everything, like distribute, simplify, combine like terms, and then you got standard form. From vertex to factored form, you have to first turn the vertex into a standard form and then factor the standard form until it gets to factored form. For factored form, to get to standard, you just do it like the vertex form. You distribute, combine like terms until it looks like standard. And then for factored to vertex form, you would have to first find the vertex of the x value of the vertex, and then find the y value of the vertex, and then match that formula to the vertex formula. And these are all the ways that they change between each other. I will tell you the useful ones that you should definitely know how to do that is worth your time is simplifying into standard form from vertex and factored form, and going from standard form to factored form. The three other methods here, while they are doable, they're not necessarily useful. Even if it's good to have that knowledge, turning what you have into the designated form isn't going to give you more information, because for standard form, turning it into the vertex form just gives you numbers that you would have already figured out if you knew how to work with the standard form. And same with factor to vertex. Look at all that work. We don't need all that. We can find the vertex form just through the methods that go with the factor form. This is how the different types of quadratics relate to each other, and understanding how they all interact with each other is going to be really helpful. And we move. Before we go into trying some tough problems, I want to show you how you can use a calculator to do very basic things in terms of finding important points for a quadratic. So first, let's talk about finding the vertex. I have the directions written down here, but I'm going to show you, obviously I'm going to show you with a calculator. So we have the equation 2x squared minus 8x minus 6. If this question is in the calculator section, I have the ability to literally graph the whole thing by going to y equals, and then going into and graphing it to x. The variable button is this point, this one right over here. We're going to square it, minus 8x minus 6, and that's going to be our equation, and we can graph it over here, and then it'll show us a nice picture of it. And what you notice in this case is that the vertex has to be, in between these 2 points. It's probably down here somewhere. And what you want to do is make sure that your your graph covers that point that you're looking for. So then in this case, I needed to go down more. So what you can do is click on Windows, and this right here gives us the X bounds and Y bounds. I know in this case, I want the graph to be able to go much lower. So I'm gonna change that minimum Y value to like -30. And I'm probably overshooting it, but all I want to do is be able to see the point. So y equals -30 is fine. And now when we look at the graph, perfect. It shows you the point that we're looking for here. So because this is an upward facing parabola, the vertex I'm looking for here is actually a minimum. So then you go into second trace, which is how you click the calculator button. See that little blue calculator there? We're gonna look for the minimum in this case. And they're going to ask for a left bound, which is an x value that's to the left of that special point I'm looking for. And they're going to ask for a right bound, because I'm not going to be able to move this cursor into that exact point because everything's moving by decimals. So the calculator is asking you to give them a range of x values so that they can estimate exactly where your point is supposed to be. So my right bound, I want a x value that's to the right of the point I'm looking for. And 2, negative 14 is the point of my vertex. And this is an upward facing parabola, so then I looked for a minimum, and likewise, if it's a downward facing parabola, I would be looking for a maximum. And now that we've gotten the vertex, let's try to find the next thing that's relatively pertinent, which is the x-intercepts. I mean, the y-intercept. I can just look at this and be like, negative 6, we're done. The x-intercepts is a slightly different way of doing it, but we still do it through the calculator. First, we're going to go into y equals graph, which that part we already did. We know the graph already captures the 2 x-intercepts we're looking for. We're just looking for those points. So that part's also already done. So now we're going to go into second calc. And notice that they don't have any options that says x-intercept, but there is this word right here, 0. And remember how zeros and x-intercepts mean the same thing. So that's what they're referring to when they say zeros. And this time, notice that we're looking for 2 points. So then I'm going to have to do this process twice. And let me get the point on the left first. Notice that if I try to click the left and right button thingy, it takes me a while to get there. So what you can do when they ask for a left and right bound is you can literally just plug in the number. I know this point right here is to the right of like -1. So then my left bound could just be -1. And then you see how they do that for you automatically. And the right bound, I know this point, now I just want to point to the right. So then I can say x equals 3. And now that I have those 2 bounds, they're going to figure out for me exactly what this point is. And now I know that one of my zeros is negative 0.64 or 0.65. And then when I want to find the other 0, I just repeat the same process. Second calc, option 2 is 0. And then left bound, you want to make sure you're not putting it to the left of the other point that you want. So my left bound, I'm going to make 2. And then the right bound, we're going to go with 1, 2, 3, 4. So this is 5. X equals 5 is to the right of where the x-intercept is. So then we'll just do x equals 5 for my right bound. And now when I click enter, this will give me 4.65. So then the other x-intercept is 4.65. And those are some ways you can use the graphing calculator to get that necessary points quickly. And now let's try our 2 tough problems of the day. Okay, D, we have a rectangle is formed by connecting 2 points on the x-axis with 2 points on the graph of y equals negative x squared plus 16. If the rectangle is 4 units wide, what is the area of the rectangle? So this feels like a rough problem because it combines geometry as well as algebra. But the concepts are relatively simple. You just have to make it look simple to yourself. So this is one of those situations that you definitely want to represent by picture. When you guys take the test, they're not going to provide you with a graph sometimes. So I'm going to do this problem with no graph. And we're going to just try to do as much as we can as we go and make it look as easy as possible as we go. So first of all, I want to graph y equals negative x squared plus 16. And the fact that it's negative means it's downward facing, and I know my y-intercept is at 0, 16 already. So 0, 16 is my y-intercept. The fact that there's no bx over here means that when I try to find the vertex of my x value, it's just going to be 0 divided by something. And the fact that it's going to be 0 divided by something tells me that the x values of the vertex is going to be 0. So then the y value of 16 right here is my vertex. And with that in mind, we know it's going to be facing downwards, and I want to get to my x-intercepts. And they made this equation relatively easy on purpose. What value of x is going to give me a 0 in this case? Well, 4, because I'm trying to figure out how to get this to equal 0. So then plugging 4 in there is going to give me a negative 16, which zeroes out the equation. So that's how I know my 2 zeros are here. And now that I have this curve, we can try to address the rest of the problem. A rectangle is formed by connecting 2 points on the x-axis with 2 points on the graph. An important thing to remember is if I'm making a rectangle up in here, that means the width here and here are exactly the same, and the height here and here as exactly the same, which works for my symmetrical graph, because I know that the left and right, the y values to the left and right side of my vertex is going to produce the same y values, which is also shown here and here and here and here. And they are telling me that the rectangle is 4 units wide. So the rectangle is 4 units wide. To find the area, I really just need the height or the length of this rectangle right here. And something that we know is that if this width is 4, and we know that this is going right through the middle, then these two distances are 2 and 2, meaning that the x value here, where the rectangle is 2 and negative 2. And if I want to find the height of this rectangle, then I can literally just shove 2 into the equation. In which case, notice that the 2 is in parentheses, and we do the exponent first. So then this is negative 4 plus 16, which gives me negative 12. So this point right over here is 2 positive 12, not negative 12. And this point right here would be negative 2 positive 12, because it's supposed to be symmetric. And now we know that the distance between 0 and 12 is just 12. So now I actually have the length as well, and we can multiply the 2 to get to the area. And that would be my final answer. This problem feels tougher, not because we're dealing with tough concepts, but because we're mixing concepts of geometry as well as concepts of algebra. But as long as you can represent the information to yourself as easily as possible, it's usually not horrible. And we got one more for the day. So our last problem is E. We have a giant word problem, and we want to figure out which one of these equations match with the situation. So, and we know that's the case because we read the question first. Which equation represents your distance from the ground as a function of time? So we're trying to write a function of time based on distance. That gives us the distance from ground. And for a situation like this, it really pays to have an understanding of what the graph is going to look like. We have a bungee jumper leaps off a cliff 122 meters from the ground. Her cord, when fully stretched, is 72 meters long, and it takes 6 seconds after the jump for it to fully extend. Distance between the jumper and the ground as a function of time can be modeled as a quadratic function, which equation represents her distance from the ground. So even though I already have a graph, I'm also going to draw the situation out because I think it's a confusing situation. And drawing things out really pays off. So I start at a height of 122 meters, which I can think of as my y-intercept. And that information is not helpful because between A, B, C, D, the C value is always 122. We know it is going to be a upward facing parabola because the t squared is positive. So once again, looking at the answer choices here, up on first glance, it doesn't really tell me much because they all tell me that the parabola is going up. But now let's try to find some values. So they're telling me that 6 seconds after the jump, it fully extends. So after 6 seconds, this person's on the ground now, or not on the ground. That's morbid. He's hanging in the air. And at 6 seconds, the rope is fully extended, which means that he's 72 meters lower than where he used to be. But that's not exactly what f of t equals. Okay. So f of t is supposed to represent the distance from her distance from the ground. And her distance from the ground, when you look at this picture, isn't the 72 meters, it's this distance, right? Which means to get that distance, I have to take the 122, subtract by the 72, and then recognize that at that point, f of t is actually equal to 50. So one coordinate we have in this situation is 6, 50, which is at this point something we can plug into each equation to find out which one contains the point 650. And I will show you a shortcut to do this quick, and then we'll talk about something a little bit different. Talk about a method that's a little bit different. So if you take this into the calculator, we know that we're trying to plug in 6 and we're trying to get to 50. Okay, so I would be doing 6 squared minus 12 times 6 plus 122. And I'm just checking A right now with the t squared minus 12t plus 122. And then when I click enter, it gives me 86, which is not the point we're looking for. So then that's how I know A is a bad answer. And option D here is actually the same thing. So we know that that one's not the answer either. And and now we're stuck between 2t squared minus 24t plus 122 and 2t squared minus 28t plus 122. And rather than literally retyping this into the calculator, a trick that you should use is second enter, which lets you copy everything you plugged into the calculator last, and you can move the cursor around. And when you click second delete, it lets you put values in front of the spot that you click second delete on. So if I do 2 times, it shows up before the 6. And this time, instead of minus 12t, we're doing minus 24. And this time, that's the point that gives us 50. So then that's how we know that B must be the final answer here. And that is one really good way to use your answer choices to help you find the correct equation the moment you find one good point that's distinct. Now, a slightly different way to handle this problem is to do it based on a better understanding of the form of an equation, of a quadratic equation. So we know with a bungee cord that like once it bounces, once it reaches maximum length, what it's supposed to do is it's supposed to pop back up. So that when t is greater than 6, like t is 8 or something, that distance from the ground is actually higher than 50. And if that is the case, where first it's going downwards and then it's going upwards, and we have a quadratic equation representing the situation, that tells me that 650 is not only a point we know exists on this quadratic, but it's also the vertex. Okay, and knowing that 6 is the vertex, 650 is a vertex means that I know that the x value of the vertex is supposed to be 6. And if you remember for standard form that 6 is supposed to equal negative b over 2a, you can knock out a couple bad answers already, where for c, if you do negative of negative 28, that's positive 28 divided by 4, that is not 6. And now you're stuck between A, B. From here, you get to plug in a value of 6 into each one of these parts again, and then that's going to give you the correct answer. So having a better contextual understanding of the situation and understanding how it equates to the graph of the quadratic is also something that helps you narrow out bad answers, so that we know at the end that B is the correct final answer here. And with that, we are done for the day. Hope you guys learned some quadratic stuff today.